Good morning, ma'am. Myself, B. Anil Kumar from CSC section. My topic is stochastic policy search. Stochastic policy search, advanced method for learning optimal decision-making policies in complex, uncertain environmental through stochastic optimization techniques. Introduction to stochastic policy search. Stochastic policy search involves optimizing policies that output probability distributions over actions rather than deterministic actions. It is commonly used in reinforcement learning to handle environments with uncertainty and complex dynamics. The goal is to find a policy that maximizes expected reward through probabilistic sampling methods. Motivation for stochastic policies. Stochastic policies enable better exploration in large or continuous action spaces. They can improve robustness against noise and partial observability in the environment. These policies often lead to more stable learning compared to deterministic approaches. Basic concepts of policy search. Policy search method directly optimize the parameter of a policy function based on performance metrics. The policy is typically represented as a probability distribution parameterized by neutral networks or other models. The optimization process adjusts these parameters to increase the expected return from the environment. Probabilistic policy representation. Common representation include Gaussian distribution, softmax functions, or more complex stochastic methods. The parameter of the distribution defines the mean variance or other characteristics of the action probabilities. This probabilities approach allowed for flexible and adaptive action selection strategies. Core concept overview. What is stochastic policy search? Stochastic policy search represents a class of reinforcement learning algorithms that directly optimize policy parameters through sampling based methods. Unlike value based approaches, these methods operate in the policy space, making them particularly effective for continuous action domains. The stochastic nature allows exploration through rodents in action selection, enabling robust learning in high dimension noisy environment. Key characteristics: direct policy parameterization without value action approximation, gradient free or gradient based optimization strategies, natural handling of continuous action spaces, robust to local optimal through stochastic exploration. Space efficiency varies by algorithm design. Fundamental approaches: gradient based methods, policy gradient algorithm compute gradient of expected return with respect to the policy parameters, reinforce PPO and TRPO leverage gradient information for efficient parameters updates. Evaluationary strategies, population-based optimization techniques that evaluate multiple policy candidates simultaneously. CMA, ES, and genetic algorithm explores the parameter space through mutation and selection. Black box optimization derive free methods like cross entropy method and neutral evaluation strategies that optimize policies through iterative sampling and ranking without gradient computation. Policy gradient framework. The policy gradient theorem provides the mathematical foundation for gradient based stochastic policy search. Mathematical properties. The gradient estimator enabled direct optimization of the expected cumulative reward by sampling trajectories from the current policy and weighting long probability by returning we op- obtained unbased gradient estimates. Variance reduction techniques like baselines and advantage functions and important sampling significantly improve simple efficiently and coverage stability. Algorithm comparison reinforcement pole pro TRPO CMA ES natural ES exploration exploitation trades off entropy regulation adding entropy bonus to object encourage diversion action selection prevention permutation coverage suboptimal policies parameter space noise injecting noise directly into policy parameter rather than action space create temporarily correlated exploration that more effective for control task adaptive mechanisms dynamic adjustment of exploration rates based on learning progress and uncertainty estimate optimize the exploration exploitation balance through training. Advanced techniques trust region methods TRPO and PPO constantly policy update to prevent destructive parameter changes subject to KL divergence constraints ensure monotonic improvement. This guarantees stable learning even with large neutral network policies. Natural policy gradient using the Fisher information matrix for gradient update provides inversion to policy parameterization. Natural gradient follows the steepest accident action in the space of probability distribution, improving convergent properties. Application domains robotic control continuous control of high DOF manipulators and locomotion systems. Stochastic policies naturally handle uncertainty in dynamic and sensor noise. Autonomous navigation, path planning and decision making in dynamic environment, stochastic exploration crucial for discovering safety efficient strategies. Game planning strategies decision making in particularly observed game stochastic policies provide unpredictability advantage maintain adaptive optimance. Implementation and consideration policy architecture selection choose neutral networks architecture approach for observe observation space, CNN for visual input, MLP for low destination state, RNN for partial observability, output layer parameter action distribution, catalog for discrete, hyperparameter tuning, critical parameters including learning rather, batch size, discount factory UI, and entropy coefficient start with established baselines and adjust based on reward signals, versions, and convergence behavior. Use learning rate scheduled for stable relay stage training. Computational resources. Parallel strategies collection deterministically improve sample efficiency. Distributed training across multiple environmental enable particular application to complex domains. GPU acceleration essential for large policy network and high dimensional observable spaces. Key takeaways: direct policies optimization. Stochastic policy search method optimizes decision making policies directly without intermediate value functions offer advantages in continuous action. Diverse algorithm family range from the gradient based approach PPO, TPO, TRPOs to evaluationary method, each with a distinct trade-off in simple efficiency, stability, and scalability. Practical importance: improve success in robotic autonomous systems and gameplay, demonstrate real-world applicability of these principle reinforcement learning techniques. Thank you.